Hello, my name is Jayati Deshmukh and today I'll be presenting a demo paper titled An Interactive Simulator for COVID-19 Trend Analysis for CoDS-COMAD 2021. This is the overview of the presentation. I'll give a brief introduction. Next, we'll check the extended SEIR model. We'll see Bangalore and Karnataka level features of the simulator, and then we'll see a quick demo of the simulator. And finally, we'll conclude with some of the future directions. So let's get started. As we all know, currently we are all in the middle of this global pandemic called COVID-19, and a variety of strategies are being tried out in order to limit and control its spread. Now, simulation is a very useful technique using which one can try out various strategies or scenarios and observe what will be its effect before actually implementing these technique in reality. With that regard, our interactive COVID-19 simulator combines three aspects. One is the underlying SEIR model, and next it also brings in network diffusion models and community interaction models. And as we'll quickly see in the demo, it is very easy to simulate a variety of scenarios on the simulator. And it also generates interactive heat maps highlighting the spatial distribution of the spread and line plots showing temporal evolution of the disease. This is how the extended SEIR model looks like. It has basically these 6 states. Initially, most of the population is in the susceptible state, and when these people come in contact with someone who is infected, they move to the exposed state. From the exposed state, people can either move to symptomatic state when they show severe symptoms, or asymptomatic state when they have mild or almost no symptoms. And from here, they can transition to either recovered or dead state. So this is how the overall model looks like. Next, these are the different model parameters, things like the transmission rate, various transition rates from each of the states, and so on. And the default parameter values we have taken from this India size sim. And we are also in process right now to learn these parameter values based on a variety of data sets which we have. We run the simulation at 2 levels, at Bangalore city level and Karnataka state level. And underlying, there is a graph which we built. And at city level, each node of the graph represents a ward. And at state level, each node of the graph is a district. That is the underlying graph. And then it is observed that mobility plays a crucial role in how the disease spreads within a city. Basically, any city can have 2 types of mobilities. One is short distance mobility, where people commute to places nearby their home for things like grocery or other daily essentials. For this, we connect all the wards within 1 kilometer distance of the current ward and add this short distance mobility layer. And the next kind of mobility is long distance mobility, where people commute to offices, schools, universities, or sometimes even for community interactions like theaters, malls, temples, and so on. For this, we have used 2 kinds of data. One is data from Facebook GeoInsights portal, and one is data from BMTC. So we add these mobility layers on top of the underlying graph, which we discussed. And apart from mobility, we also model different kinds of interaction parameters at the ward level. What we observed was that every ward has a different characteristic. Some wards may be residential, some wards on the other hand might be commercial with office spaces and so on. And based on these characteristics, they can have different kinds of interactions, right? Workplace interactions, community interactions, and so on. And these interactions can vary across wards, and this in turn will have an effect on the exposure rate at that ward level. Thus we use all these different kinds of interactions characterizing the wards and aggregate it using this weighted softmax function and compute a exposure rate for each ward level, and then run on the simulation and observe how the trends look like over the city. So this was for Bangalore level. Next, let us discuss at Karnataka level. So here we create a district level graph where each district is the node and all neighboring districts are connected. Also, to calculate exposure rate, we have focused on data coming from fever clinics. So fever clinics are basically a first point of contact for anyone who is suspected of having COVID. So people having symptoms like fever, cough, cold, sore throat, etc. They first go to a fever clinic to get tested, and from there they are referred to, let's say, a COVID hospital or a quarantine center or things like that. So we basically take the ratio of total referrals from a fever clinic divide by the total number of tests done there at that fever clinic, and that is this metric we take as the exposure rate. We aggregate it at a district level for all the districts in the state. So next, let us move on to the simulator demo. So this simulation can be either at Bangalore city level or state level. Let us start with city level simulation first. So we select Bangalore. We can select one of the start dates and we can run the simulation for selected number of days. So let's say we scroll it to 50 days. Next, these are the different interaction parameters. So things like workplace interaction, community interaction. Let's say mostly schools and colleges are closed, so we can decrease the school interaction. We can vary all these parameters based on the scenario. Then there can be different levels of mobility. So let's say we increase this mobility level across the different wards. Next, we can add BMTC edges and Facebook edges as required. And then these are all the SEIR parameters. So let us plot based on the selected values. So yeah, this is how the heat map looks like. We can plot all the 6 compartments from the SEIR model, and then we can vary over time and see how it changes. So on the right, we can see the top 10 wards with the selected metric. Here, it's infected symptomatic on, let's say, day 17. And then it also shows top 10 wards with most growth of this selected metric on this day. So yeah, we can vary this and see how the trends change over time. So this was the spatial spread of the disease. Next, let us see the temporal spread. So here we see the line plot of all these 6 compartments, and we can plot it either at logarithmic scale or linear scale. And the current plot is at Bangalore city level, but we can select a specific ward, let's say Jakkur or HVR layout, and there we can see the plots change specific to that ward which is selected. So this is how it looks like for city level. Next, let us run the simulation for state level. So again, we select Karnataka, we can select a start date, and let's again run it for 50 days. We can change the SEIR parameters if required. So let's plot. So right, this is how it looks like. Now let us maybe see how the recovered numbers look like. So we can again change, scroll this and see how it changes over time. On the right, we see the top 10 districts with recovery numbers, and then the top 10 growth in recovery numbers. So these are all those districts. And even for a specific district, we can see the exact numbers on the right. Below, we see this again line plot for all these 6 states, which can be again linear or logarithmic. So again, this is at Karnataka level, but we can see for a specific district as well. So let's say if we select Bangalore urban, this is how the predicted trends look like, and we can try out for various districts. So this is how it looks like for Mysore. And yeah, so this was a quick overview of our COVID-19 simulator dashboard. So thus, with that, I'll conclude. We observed that the simulator combines 3 aspects, basically the extended SEIR model, and then we bring in network diffusion models and community interaction models. The simulator can simulate variety of scenarios like deferred workplace interactions, closing of schools, like different levels of public transport, mobility levels, and so on. And it can also generate interactive heat maps and line plots by predicting the potential spread of the virus. It can provide key insights to develop actionable measures to control or delay the spread of the disease. In future, we also want to incorporate actual versus predictive trends in the plot, so that one can compare how the results look like to the actual numbers that have been observed in the past. And we can also extend it to other cities or states, given based on the availability of the required data, which is needed in the backend. With that, I'll conclude. Thanks a lot for listening to my talk, and I'm very happy to take any questions. Thank you.